This module examines the robot's subsystems, such as the number of axes, the driving energy sources, feedback devices, and controllers, which are needed to make modern robots completely functional. The robot's joints are called its axes, articulations, or degrees of freedom. The number of axes a robot has determines the complexity of the tasks it can perform. There are currently 3 classifications of robots: low, medium, and high-technology robots. These classes are differentiated by the number of axes and consequently the number of intricate motions the robot is capable of making. Low-technology robots may have as few as 2 axes. These robots are capable of performing simple transfer operations and are often called pick-and-place robots. The 2 axes of a low-technology robot are shown here. The robot is mounted on the work surface and can rotate around its own central axis, as well as extend and retract its arm. This is another low-technology robot. It has 3 axes, or degrees of freedom. These axes are vertical travel, column rotate, and extend retract. The term work envelope is used to describe the maximum space in which a robot can move. The work envelope of a robot which rotates on its base and extends, retracts its arm is therefore a circle. If it moves up and down on the column and extends and retracts its arm, the work envelope is rectangular. The envelope for this robot is cylindrical, since in addition to being able to rotate on its base and extend, retract its arm, it is also able to move up and down on a column. This is known as a cylindrical coordinate low-technology robot. This is yet another low-technology robot with base rotate, extend, retract, and vertical pivot axes. This robot is called a spherical coordinate robot because its envelope defines a portion of a sphere. Low-technology robots are used for applications such as material handling, press operations, machine loading and unloading, and in simple assembly operations. The low-technology robot is very important to modern industry since its limited versatility is all that is needed in simple pick-and-place applications. Its low cost, compared to the more sophisticated robots, makes it desirable for simple operations. The medium technology robot is characterized by the added versatility of more degrees of freedom, or axes. This medium tech robot has 4 axes: extend, retract, left to right swing, shoulder elevation, and wrist bend. Another medium tech robot can have a movable elbow instead of shoulder elevations. This one has wrist yaw, or sideways movement, in conjunction with wrist bend. These medium-tech robots are called jointed spherical coordinate robots because their envelope approximates a spherical shape. With these added degrees of freedom, the medium-tech robot can perform more complex tasks, such as spray painting operations. In spray painting, the robot arm must swing from side to side while the wrist manipulates the spray gun. The more complex and consequently more expensive medium-tech robot can handle jobs where material must be turned or otherwise manipulated, in addition to picking up and placing the material where it is needed. The most versatile and technically sophisticated modern robot is the high-technology robot. Robots in this class have 5 to 10 degrees of freedom. This 10-axis robot can follow an automobile down an assembly line, reach inside to weld the required points, then return to the beginning of the line to wait for the next automobile. The Unimation Puma 250, 500, and 600 series robots are high-technology robots which make use of 5 to 6 degrees of freedom, excluding the motions which may also be available in the gripper. This Puma 600 robot has 6 axes in its arm. This robot is called a jointed spherical coordinate robot because its working envelope is almost a complete sphere. The dimensions of the Puma 600 series robot arm are closely approximate to those of the human arm. High-tech robots are sufficiently versatile in their motions to do complex jobs such as printed circuit board assembly, adhesive application, and material inspection when equipped with optional sight capability. Energy is needed to impart motion to the robot's axes. Common sources of energy used in robotics include pneumatic, hydraulic, and electric power sources. Each joint of the robot arm needs some type of drive system to impart motion to the joint. This drive system may be pneumatic, hydraulic, such as the one shown here, or some combination of these. Pneumatic systems are commonly found in the fast-operating, low-power, limited sequence or low-tech robots. Compared to all other drive systems, pneumatic systems are generally the most reliable, thereby decreasing possible maintenance costs. However, the speed and position of a pneumatic system can be difficult to control. Pneumatic drives are therefore used primarily in the less precise pick-and-place, limited sequence robots. Hydraulic drive systems provide greater physical power and more accurate control than pneumatic systems. Hydraulic drive system components come in two distinct categories: actuators and motors. Of all the hydraulic drives, the piston actuator is the simplest, most reliable, and least expensive. Hydraulic motors provide better performance but cost more. Electrical drives consist of rotary motor actions. Some typical motors used in robotics include servo motors, stepping motors, pulse motors, and linear and rotational solenoids. Motor-driven robots, in general, have higher maintenance costs than the comparable hydraulically driven robots. This is due to the high cost of components and the normal wear in shafts and bearings. Hydraulic drive systems can present leakage problems. Oil leaks are usually progressive, but easy to spot, and can be repaired conveniently with little machine downtime. Also, hydraulic drive systems must periodically have the fluid and filters changed and require a warm-up period before operation. Various feedback devices have been used to supply the robot's controller with the necessary positioning information. With such feedback data, the computer and/or controller can make calculations and, consequently, send very accurate positioning information to the robot arm. The simplest of feedback devices consists of varying an electrical parameter as a function of the position of a robot axis. For example, the moving joint can position the contact arm of a rheostat, the magnetic slug of a coil, or the dielectric of a capacitor, thereby producing an electrical parameter change which can easily be detected by electronic circuitry. Strain gauges, or load cells, mounted in the robot's gripper can be related to an electronic circuit so that the gripping pressure of the fingers can be controlled to allow delicate materials to be handled by a robot without damage. A robot equipped with video camera sight capability can see if the material to be handled is oriented properly for the present position of the end effector. This video information enables the controlling computer to provide the proper control signals to reorient the hand if needed. Electrical limit switches mounted on the robot's various axes can be used to monitor maximum positional information so that the controlling computer does not force a joint past its physical limit. Pressure and vacuum switches can also be used to relate the position of a robot axis to the controller by creating a proper feedback signal for use in pneumatic and hydraulic systems. The information sent to the robot's computer by a broken photoelectric beam system can be used to inform the system about the actual position of any of the robot's axes. Infrared detection systems are used to give the robot the ability to sense the presence of heat. This information feedback can give the robot the ability to select only those materials which are at the proper temperature for subsequent handling. Ultrasonic sound systems can be coupled to the robot control system to give the robot the capability to sense motion and measure distance. The signals that actually make the robot's various joints move are created by the robot's controller. The controlling signals can be electric, pneumatic, hydraulic, or a combination of these. The primary distinction between robots and hard automation devices is the robot's ability to learn. Here, the robot is learning how to weld a door. By learning, we mean that the motions the robot will ultimately perform are placed in some sort of memory. Then, by recalling the contents of the memory, the robot will act predictably. The controller used for some robots is actually a computer. A program is a list of instructions in the computer which directs all of the robot's motions. Air logic controllers perform their control functions by activating small valves arranged on a sequencing module. Here, the memory function is performed by the preset position and sequence of motion of the valves. This module has examined many of the robot's drive systems, including its axes, the 3 types of drive systems and controllers, and feedback devices which can be used to assist in properly locating the robot arm within its work area.